Okay, so this lesson today is over periodic trends. So make sure you have the notes to follow along. You should have gotten those on your way in. And we're going to look at the different trends that we have and we can see on our periodic table. Trend number one is going to be atomic radius. And so the atomic radius of an element is the measure of the size of the atoms. It's typically the distance from the nucleus to the edge of the electron cloud. And so, based on where an element is located on the periodic table, it can tell us a lot about its atomic radius. If we look at a periodic table, what's going to happen is the radius is going to decrease as you move from the left to the right, okay? And it's going to increase as you move down the group of the periodic table. And so this picture just kind of shows you atomic radius or the size, right, based on this location. And so as we go from right to left, it increases, and from top to bottom, it increases. So atomic radius is going to increase from right to left and top to bottom. The largest element on this picture would be cesium. The smallest element on this would be helium. Okay, so atomic radius is our first trend. It increases from right to left and down the group. So on this chart or this picture, you can see, right, your atomic radius increases as we go down and from right to left. So this element down in the bottom corner is going to be the largest. The one up here, which is helium, is going to be the smallest element. So here we have a learning check just to kind of see if you're getting this right. And so it says, which atom has the larger radius? And so you're going to look on your periodic table, and the hint says who's closer to francium or francium, right? And so if we look, we have sodium, we have cesium. Cesium is definitely closer to francium, and so therefore cesium would be the correct answer. Okay. The next one, we want to know if it's sodium or sulfur, right? And so we look at our periodic table. Sodium is going to be further to the left, so therefore sodium is going to have the larger atomic radius. And then we look at oxygen and sulfur. Oxygen's higher than sulfur. Remember, it increases down the group, and so therefore sulfur is going to have the larger atomic radius. So make sure you get those down in your notes. Okay, so trend number two is going to be ionic radii. An atom gets bigger when electrons are added, and atoms get smaller when removed. And so that's what we're looking at with ionic radii. Um, you're not going to see a whole lot of ionic radii, but we still cover the trend. And so the trend is it's going to decrease as you move from right to left and increase as you move down the group. Okay, so increase as we move from left to right, but decrease as you move down the group. That's ionic radii. So it's basically the same, right? Same as atomic radii. So once again, atomic radii and ionic radii are pretty much the same trend. Moving right along, trend number three is going to be ionization energy. An electron can be removed from an atom if enough energy is used. And how much energy? Well, that's what we look at when we look at ionization energy. It's the energy required to remove one electron from a gaseous neutral atom. And so it's how much energy that we need to actually remove an electron. Okay, if you look, we have this picture down at the bottom. It has the trend, and so it's going to increase from bottom to top and from left to right. Metals freely give their valence electrons, right? So they cost less energy. Nonmetals hold on to electrons more strongly, so they must pay more energy to get rid of them. Okay, so metals are going to give their valence electrons freer, right? So they cost less energy. Non-metals are going to hold on to those more strongly, which is why it increases from bottom to top and left to right. If you look at this picture, it shows you, so as we move up the group and from left to right, it's going to increase. So ionization energy increases from left to right, and as you move up the group, it also increases. Notice that our noble gases have really high ionization energies because they don't want to give up those electrons. So if we look on this picture, right, we've already said atomic and ionic radii decrease as we go down and from right to left. Ionization energy is going to increase up the group and from left to right. So if we look, we want to know what has the higher ionization energy. So the first one, right, lithium or fluorine. If we look at that one, okay, lithium is a metal, right? So it's going to have a lower ionization energy. Plus fluorine is further to the right, okay? So fluorine is the right answer because it's further to the right. Remember, we increase from left to right. Then we have potassium and sulfur. So with that one, sulfur is going to be further up and further to the right. So sulfur is definitely going to have the higher ionization energy. And then barium and lithium. We look at barium and lithium. Okay. And so lithium is definitely going to be the greater ionization energy because it's higher than barium. Moving right along. Trend number 4 is electronegativity. So this applies when an atom is a compound and not alone. Electronegativity measures how strongly an atom attracts electrons when it's in a compound. So how much of a bully that element is in a compound. Think of your atoms as little kids, your electrons as toys, right? Fluorine is going to be the most electronegative element. It's assigned to number 4, which is the highest. Okay? So fluorine's going to want to hog those electrons, right? It's going to be the bully. Before we move on, I do want to mention that notice it says fluorine is the most electronegative element. Now, why is fluorine the most electronegative and not helium? Well, we just said that electronegativity is how strongly atoms attract electrons. Do noble gases attract electrons? No, they don't, because remember, noble gases are already satisfied. They're not going to gain or lose any electrons. And so because they don't gain or lose, that means they're not going to have an attraction for electrons. And so noble gases like helium, neon, argon, krypton, xenon, and radon are not going to have an electronegativity. So if you see a question that says one of the noble gases has the highest electronegativity, that's wrong because they don't actually have electronegativity. So keep that in mind. Our trend for electronegativity, very simply, okay, it's going to increase from left to right, and it's also going to increase from the bottom to the top, okay? Notice that your notes say it's going to increase across the period from left to right, but it also says decrease down the group, which means it increases up the group. So increase from bottom to top and from left to right. So electronegativity is the same trend as electron affinity on this picture, right? So remember we said atomic radius decreases from right to left and then down, right? Atomic and ionic radius are the same. And we have ionization energy increases from the bottom to the top and from left to right. And then we just said electronegativity increases from bottom to top and left to right as well. Okay, so which has the higher electronegativity? looking at the first one, okay, we have strontium and we have beryllium. So strontium and beryllium, we look at it on our periodic table. So beryllium is higher in the group, and so therefore beryllium is going to have the higher electronegativity. Then we look at phosphorus and oxygen. Oxygen is higher and further to the right, so it's going to have the higher electronegativity. And then we look at silicon and chlorine. Chlorine is further to the right, so it's going to have the higher electronegativity. Remember, electronegativity increases from bottom to top and left to right.